So there we go. But again, fractions are the most common. We can use a colon as well, means the same exact thing. But that's how we define a ratio. All right, so when we now go to this, it says here's a picture of rectangle R, which has been evenly divided into smaller rectangles. All right, and then two of those rectangles are labeled as B and C. So what we want to understand, rectangle R is this big one. And then we have all these other rectangles. We've labeled two of them. So what number one is asking you is B a scaled copy of R? All right, and if so, by what ratio? So here's what this is alluding to. If I now look at letter B here, so this triangle here, what that is really asking you is, what have we done to all of their side lengths? All right. So we want to know if B is that copy. So look at this blue length here. If I told you that this blue length was 20, all right, the top of rectangle R. When we look at rectangle B, what would it appear rectangles B's top height is, or top length is? Yeah, wouldn't that be 10? Let's say I would have told you rectangle R, so this big one, its side, we'll say, let's say this is 16. What would it appear based upon our graph that the side of rectangle B is, that corresponding left-hand side? It would appear to be what? Hannah? Yeah, isn't it half? Right? We agree with that? So it's similar to the question that we just finished with. The two those trapezoids, what did we do to go from one to the other? So if B was a copy of R, that means R was the original rectangle, and then B was a copy of R. What have we done to the lengths of R to go from the side of R and then to make a new rectangle B? What have we done to all of those sides? Yeah, we divided by 2. So because all of them are the same, you're going to say, yes, this is, and it is because there is a common ratio. Hannah said divided by 2, 100% correct. As a ratio, we're going to write that as a 1/2. We basically did 20 times 1/2 to get that here. We would have done whatever that side length is, cut it in half. That would have given us the side of rectangle B. All right. Okay, we all see that. Makes some sense, hopefully, Riley. Okay. Number 2 then. Let me erase that stuff so we can kind of focus on the 2 that we're concerned about. So now find those 2 rectangles. So letter C is now down here, and we want to know, is that a scaled copy of R? So same idea. I guess I didn't need to erase R. So here is R. This one's a little trickier to see. You got to be a little more clever here. Same idea. Let's say, let me label it on the bottom though. Let me label the bottom of this. Let's say rectangle R. I'm just making this up, so don't ask where I'm getting it from. Let's say this, actually not, let's let me not use 20. Let's say this is now 24. Do we agree that this would have been 12 and then this whole thing here would have been 12? Right? That got cut in half. Well, we don't want the whole thing. So this length here is 12. This length here is 12. If this whole thing is 12, what is the length of the bottom of just C right here? Hannah, what would that have to be? Good. Wouldn't this have to be a 4 so that I'd have 4 here, 4 here, 4 here, and that would give me 12? So think about what we just did. Rectangle R was 24. That's the bottom of rectangle R. And then this little rectangle C got moved down to a 4. Hannah said divide last time. We can go with that initially here. What would we have divided 24 by to get down to a 4? A 3. A 6, right? 24 divided by 6. Doesn't that give us the 4 that we ended up with here? Wouldn't that mean our common, oops, this is for number 2. You're going to say, well, we'll do the other one here in a second. Doesn't that lend us to believe that our common ratio is 1/6? That side is 1/6 of the other side. Let me just show, because it's got to be, all the sides need to be the same. So now let me go to the right-hand side. Let's say this right-hand side was, say, 18. Do we agree that then from here to here would have been 9? And then from here to here also would have been 9? What does the length of rectangles C's right-hand side have to be? So what would this guy right here need to be if all three of these were 9? Now that's what, Hannah? Good. Wouldn't this have to be a 3, 3, 3? So isn't rectangle side 3? Isn't 18 divided by 6 going to give us that 3? So isn't that common on both sides of that rectangle? So that then confirms that, yeah, they're the same ratio, and that ratio is 1/6. Okay. All right, letter C, last one here, or number 3, which is dealing with letter C. Try that one, see if we're understanding this. This is not easy to see. This is, again, there's a reason we're going to spend a few days on this. So find little rectangle C, but now you're going to compare it to rectangle B. What did we do to B? Because B is obviously bigger than C. How did we take rectangle B and reduce it down to the little rectangle letter C? All right. Can get it? That's pretty good already if you're able to see that. This is also a little tricky. Okay, if you got it, that's really good. All right, so here is rectangle B, right? And we wanted to know, is C a copy of B? So if this is now our original, how did we take this big rectangle B and reduce it down to this smaller rectangle? Anybody feeling really lucky? What do you got, Hannah? Very good, Hannah. How'd you get that, Hannah? Where'd you get the 1/3 from? Say that one more time now. So like if you made like rectangle R 12, and then B would have been 6, and C would have been 2. Okay, so she kind of used some numbers like I did to rationalize all of this. So she said this was a 12. So if she made that 12, then she understood that letter B here would have been a what? A 6. Well, isn't this guy also going to be a 6? Wouldn't this one over here also be a 6 overall? And then she knew if overall this was 6, what does each one of these 3 then have to be? Good. Those are then going to be a 2, and a 2. So she went from a side length of 6 in rectangle B, and rectangle C has a side length of 2. So didn't that mean we did 6 divided by 3 in order to get the 2? All right. So good. That should be our 1/3. Okay. If you can't see that, give it some time. We're going to do a number more of these. And that, again, it's a little tricky. You're not alone if it's a little weird here. All right. So that's kind of our ratio. That's what we're doing from one to get to the other. All right. A couple more definitions that we're going to deal with a lot. So the first one is where it says similar shape. Similar shapes need to have 2 things. All the corresponding angles need to be congruent. So we've already kind of talked about corresponding angles. We talked about congruency, things like that. The lengths won't be congruent, but their ratios all better be equal to each other. So all the corresponding lengths should have the same exact ratio. When we use the word scale factor, that's what we just did above. It's what you did in the homework. That's the ratio that takes us from one figure to the other. What did we multiply by in order to get the new figure? And then a dilation, probably a new word for most people in terms of math. A dilation is a transformation. So last year you did rotations, you did reflections, you did lines of symmetry. Those are all transformations. A dilation is another transformation that changes the side of an image. When we change the size of an image, we keep the angle measures, so those don't change. And then the sides are either enlarged or reduced by the same ratio. The ones above, we reduce them all. All right, the scale factor measures how much larger or smaller the new object is relative to the original one. And then here's our big thing that we'll be dealing with. If our scale factor ends up being less than 1, then we are going to call that a reduction. It means we made it smaller. If we go up to all of these, it was a 1/2, a 1/6, and a 1/3. All of our rectangles got smaller. We went from the bigger one to the smaller one, so that's why. If our scale factor ends up being greater than 1, that means our figure got bigger. The math word for that we would be using is an enlargement. Okay? So to kind of justify or talk about what those are here real quick, it says all the triangles below are dilations of triangle C. So that simply means triangle C is your original triangle. And then A, B, D, and E are dilations. They've been shrunk or enlarged. All right. The dilations used center P. And then it says, but they have different scale factors. So when we look at number 4, it says, what do triangles 4 and angle B have in common? What we're looking at is this idea that if this is our original one, do we agree that A and B both got smaller? Okay. So they are smaller than rectangle C. Smaller is fine. The correct geometry word, math word that we are going to use is this one right here, the word reduction. So they are a reduction of triangle C. All right, they got smaller. Five, then, if you understood 4, now that we talked about it, 5 is just the opposite. If you look at D and E are larger. So those are larger. That's kind of vocab we know. The math word we're going to use is this guy right here, though, to represent larger. That is the word enlargement. So we're going to say that these are enlargements of triangle C. So 2 of them got smaller, 2 of them got bigger. C is the original. 6, then, what does it tell us about the different scale factors used? So what you're going to put here for triangle A and triangle B, we don't know the scale factor. I don't give you numbers to work with like we did in the problems at the top of the page. But what we just said up here, if I have a reduction, then I know that my scale factor must be less than 1. So for triangle A and B, we know that ratio that we're multiplying by for sure had to be less than 1. And then the opposite of true is for the next one, for triangle D and E, the one that we said, the 2 that we said are enlargements, they got bigger. If it's an enlargement, then we know our scale factor must be greater than 1. So you're going to say R is greater than 1. All right. And then eventually we'll kind of figure out what all of those are. All right. Next one. Another opportunity then. Hopefully these will start making a little more sense. So as an actually, I won't even worry too much about that right now. Let's just worry about our scale factor. So when you look at this here, what you're going to see is 3 rectangles. They all line up down here at this corner. We have a blue rectangle, which we call B. The green rectangle is G. The big rectangle is the R. All right. Number 4, I want you to find the scale factor. The scale factor is the ratio that we would multiply by to go from one rectangle to the next. What we want to do in this one, we want to go to B from R. So we want to start at B. To R from B. So we want to start at B, end up at R. So we want to start at B and end up at R. So go to your blue rectangle. Let's start with the right-hand side of our blue rectangle right here. Notice how the right-hand side of the blue rectangle is a 2. If I look at the the right-hand side of the red rectangle, that guy is a 4. So in that case, we went from a 2 to a 4. If we go to the top of the blue one, the top of the blue one is a 4. And we want to go blue to red. If I go to the top of the red one, the top of the red one is an 8. All right. So now if I ask you what we did, what is the common ratio that took us from 2 to 4 and then from 4 to 8? And what would we write? We're 2, right? We're just doubling them. All right. That one's pretty easy. We can do that in our head. All right. Everything gets doubled. So the red rectangle gets doubled. All right. In relative size to the blue rectangle. All right. Number 5, a little trickier. We want to go 2G from B. So same idea. We want to go from B to G. Do that one and see what we think. Tell me what you think our R must be in that one. From the blue rectangle to the green rectangle. Because when they're nice whole numbers, it's a little bit easier. This one isn't nice whole numbers, a little sneakier. All right, Kat, what'd you do? What is it? All right, she says 1.5. How'd you get that, Kat? And where do you get the 4 and the 6 from? Okay, by side you mean the top here? Yeah. Okay, so the blue rectangle has a 4 on the top, and the green one has what? 6. So what she did is she understood that she had to get from a 4 to a 6. And the only way that she could do that, if you can kind of do it in your head, is multiply by 1.5. Same thing should apply right here. I have to go from 2 to a 3. And 2 times 1.5 will give you a 3. Now, if it's a weird decimal, so some people, Kat can do that in her head. Here's how we can do this if it's an ugly decimal and it's not quite as simple as this first one. If I wanted a ratio of 2, look at the numbers that we use right here. We can really kind of set up this little ratio. Whatever I'm going to is the numerator. Whatever I'm coming from is my denominator. I went to 4 from a value of 2, or I went to 8 from a value of 4. Notice how those will both give you that ratio of 2. So in this case, if we set up our fraction, I would do 6 over 4 or 3 over 2. 3 over 2 gives us that ratio of 1.5. All right. All right, 6, do 6. We want to get 2b from R. 2b from R. There's a couple different ways to approach this one. This one should be nicer. Okay, what should we get for this one? Hannah? Ooh, you're warm. Why is she warm? She said 2. Hannah? Because what's our answer? Good. It should be 1 over 2. It should be 1/2. All right. So read it carefully. Really, this is just the opposite of number 4, right? These are interchanged here. In number 4, I wanted to go 2R from B. Now I want to go 2B from R. So I want to go from the big one, 4, and I want to go down to the blue one of 2. So don't I need to cut 4 in half? The same here. The big top was an 8 and I want it to become a 4. I would need to multiply that by a 1/2 to get that 4. Okay. If you set it up and say R to B, then you're going to have 8 to 4. And then you just always put whichever one you finished with over whichever one you started with. That would also give us that 1/2. Okay. All right. Tricky stuff. This is still stuff that I got to think about a little bit sometimes, especially when they get ugly fractions here in a minute. All right, next page. It says, look at rectangles A, B, C, and D, and then E, F, G, and H. And then it says, Sam says these rectangles are similar because all of the side lengths differ by 2. So what he is saying is when he looks at this guy here and this guy here, they have a difference of 2. When he looks at the tops also differ by 2. Same with the bottoms, the 4 and the 6. All the sides have a common difference. So Sam is saying that they are similar. Okay. Question is, do we agree with Sam or do we not agree with Sam? So if we go back to our definition of similarity here, in order for them to be similar, all of their corresponding sides need to have a common ratio to them, okay? That we can multiply by the exact same number and get them to be the same. So we're going to let's do these sides first. All right, so if I ask you those yellow sides that I have highlighted right now, all right, the D to A and then the H to E. So if I'm going to do 2 to a 4, what was our ratio if I went from 2 to a 4? What did we multiply by there? All right, and Juan, what is it?
What was the question?
If I go from 2 to 4, what's our ratio that we multiplied by?
2.
2. All right, that means all the ratios have to be a 2. If I go to my blue sides then, so if I now go to these guys up here, and I now want to go from a 4 to a 6, does multiplying by a 2 take us from a 4 to a 6? No. All right. That ratio would be the 6 divided by a 4, which is 3/2. So since these guys are not equivalent to each other, we would say no. And then I didn't leave a whole lot of room to write for myself here. And that is because they must have a common ratio between all sides. And these were different. One set you had to multiply by 2. The other set you had to multiply by 1.5. All right. All right. So in that case, we're going to say no. Those are not similar. Okay. The next one, though, let's finish with these because this is pretty easy. We can do these in a couple minutes. So a similarity statement is an ordered way. The word order is important. The way we're going to order these is important of naming 2 different polygons that are in fact similar to each other. That indicates which vertices correspond to each other. Okay. So when you look at this one here, here is our similarity statement. When you see this little guy all by himself, the little squiggly, that is read as similar to. So what I am telling you here is triangle PQR is similar to triangle STU. All right. And then what I want you to do over here is match up which angles correspond to each other. So there are a couple of different ways to do this. If we just look at our triangles, do we agree that angle R, if we just kind of look and see how these are similar to each other, isn't angle R corresponding to angle U over here? They're located same kind of position within that triangle. So you're going to say angle R is congruent to angle U. Also now, look at the similarity statement right here, because eventually you won't even be given this picture. So if I kind of covered that up, we didn't have that or I deleted it. Here's how we would know this from the similarity statement. Notice how angle P is listed first here. Its corresponding angle must be listed first over here. So when we come to angle P, since P is the first angle listed in the order of this one, the S must be the angle that it corresponds to in the second one. So if I now reintroduce this picture would we agree then that angle P, which would have been down here, corresponded to angle S right here? All right. And then that graph should kind of give you the visual that that is also the case. And then the last one, if we did angle Q and T should correspond, well, look where they're located. Q was the second letter listed, T is the second letter listed, and that is because those correspond to each other graphically as well. So we would say angle Q corresponds to angle T. All right. Last thing, number 9. You can use the graph. We could use our letters. So if I look at RP, so let me clear this up a little bit. All right, so here is RP. RP's corresponding side would have to be the side U to S. So you're going to put that underneath that that's one of our ratios. RP gets compared to US. But also look at their order in which they were listed. If I look at RP, notice how R was the third one and it was paired up with the first one. And then I said that corresponds to US. Look at the way this one is listed. U is the third one and it was paired up with the first one. That's how we can do it if we just have the statement without the graph. Okay? So with that in mind, don't look at your graph. And I'm going to scratch this out as best I can here. If I wanted you to find PQ, we would just go to this similarity statement, PQ, write in on the other triangle which side would be corresponding to PQ without looking at your graph, by just looking at this similarity statement up here. What is it, Riley? Good. That would have to be ST. Why, Riley? Good. Because it's the first two in that other triangle, the way that it's listed. All right. And then last but not least, and we'll call her a day, finish this tomorrow, RQ. Notice how RQ are the second and the third ones in the first triangle. So if we go to the second and the third one in the second triangle, that would have to be one, or the side that that one corresponds to. All right. Okay, that's about where we finish. Bring this tomorrow. We'll finish this off. You're not going to get any homework. I'm going to give you the homework in class because this also just, it can be tricky and confusing. So we'll finish this tomorrow and then you'll get the homework for tomorrow. So you're free for tonight.